imagine the sampling proportion has a distribution that is going to be just as easy to work with as for x bar. It's just that this time around, you know the exact distribution of the sampling proportion. So let's discover that knowledge using the Socratic method, shall we? When you're calculating a proportion, let's take the number of you who are terribly fond of strawberry shortcake. You either are or you aren't, right? We've got 8, 14, 19. Okay, so there are 19. We ask each and every one of you if you are fond of strawberry shortcake. The answer is yes or no. Now, we're going to assume that you're all randomly sampled, which of course is false. Let's just assume that you are. We're also going to assume that we're sampling with replacement, which of course you're not in a typical sample, but bear with me. Now, if we do that, then we have independent trials. We have the same probability each time that somebody is in favor of strawberry shortcake, right? And the key point is that a proportion is calculated by taking the total number of those who are in favor divided by the total number of those absent. So really what you're interested in is the number of people who said they were in favor of strawberry shortcake. Starting to ring a bell? Independent trials, identical trials, same probability of success each time. Binomial. Very good. Now, the binomial can be a little painful if you're dealing with a very large proportion. You know, if you're dealing with something out of 10,000 trials, for instance, calculating binomial probabilities can be extremely painful. So, believe it or not, we basically come up with something that looks normal again. It turns out that if you get a very large sample size, then the binomial distribution itself looks normal. So you wave your hands and you treat the sample proportion as if it is normally distributed, but of course again you need a cutoff. This only works for certain values of n. We again have that the expected value of the sample proportion is equal to p, and the standard deviation actually resembles the binomial. It's derived from the binomial. So the standard deviation of q bar is just p times 1 minus p over n. You'll see that the square root of n is back again, but from a binomial random variable, you had that sigma squared is np 1 minus p. Right? Okay, now for the variance, essentially what that means is that you divide by n. Actually n squared. And that's where you end up with this thing. Okay. Not that that is terribly helpful. But this is terribly helpful. This is actually quite useful. This too is another not so terribly helpful. The finite population correction factor is still valid, but the same cutoff applies. You need 5% of the population in your sample before you should worry about this. Okay, so when is it that you can use what's called the normal approximation for the binomial distribution? Well, you need at least 5 in each group. So you take the sample size multiplied by p, 30 times 0.72, that's 21.6, that's at least 5. But you also take 1 minus p, 28% of 30, 8.4, it's still also at least 5. So basically you can just take the smaller of p or 1 minus p. So the magic number here is 5. The simplest way that I know to remember this is just to think, well, you have 2 groups, right? You have those who favor or want to live on campus and those who don't. Yes? every group must have at least 5. Okay? Now, this makes perfect sense if you can think of examples. If you're trying to estimate the percentage of, say, Republicans, then you're not going to need a very large sample size before you're going to find 5 Republicans and 5 non-Republicans, right? But imagine trying to estimate the proportion of communists in America. You're going to need a significant sample size, yes? If you took a sample of 1,000, how many communists would you expect to find? Maybe 0. Maybe 1, I don't know, but probably 0 would be my guess.
20.
If you took a sample of 1 million, you'd probably get a few here and there, but you know, you need some huge samples to truly get a decent estimate of the proportion of communists in the U.S. It wasn't true 75 years ago, it is true now. So, you know, you basically just have to, you can't estimate something if you're not actually observing it, I guess is the point of this story. Now, the standard error, or the standard deviation of p-bar, you can calculate it, but it doesn't have a direct analogy to a standard deviation in the parent population, the way it does for the sample mean. So we just calculate the standard deviation directly, then you get the standard error directly, and we can still calculate the probability. For instance, the probability that our sample proportion is between 0.67 and 0.77, which is the same thing as finding the probability that p bar minus p is less than or equal to 0.05. So, what did we call this? The absolute value part here? The sampling. Sampling error. Okay, so basically we're just asking what is the probability of sampling error less than 5%. But the approach is identical to what we did before, so I'm just going to show it up on this slide. The order of the thinking is as follows. You find Z, right? You look up 0.77, I'm sorry, you take 0.77 minus 0.72, which is 0.05, divided by the standard deviation of p bar, which gives you a z-score of 0.61. You look up 0.61, in the 9th edition version you would find 0.2291. In the 10th edition it would be 0.7291. And if it's the 9th edition, then you just multiply that by 2 to get a total probability of a sampling error of 5% or less of 45.82%. Any questions on that? Okay. In that case, we have just a little bit of conceptual material to conclude. These 3 characteristics are useful, but I think for the purpose of this class, it's more a question of thinking about estimators and what they are and what they're not. Unbiasedness we've already talked about. Essentially, it's just saying that the mean of your estimator is the same thing as the mean of the parent population that you're interested in, which is a fairly decent requirement, and it's quite popular. It's not always true, but usually is. As an example, actually every estimator we've seen, so for instance x bar, N, that is an unbiased estimator. So the expectation of x bar is equal to the expectation of x is equal to mu. And, okay, so if we have an unbiased estimator, what else might we want to see? What else would be useful? So we know mu is here, right? And we can pick some distribution for an estimator. What kind of distribution is most useful?
Normal.
Normal? Well, you could come up with a normal that looks like this. That's not terribly useful, is it? I mean, a normal is one candidate, but there's something else that's rather more important. Ideally, of course, you wouldn't have a distribution at all. You'd just have a constant stretching to infinity. But that's also not very interesting because then, of course, you wouldn't be doing statistics. So, normal distribution. You want one that is narrow or wide? You already said something. Narrow. Is that obvious to everyone? That this distribution is not as good as the narrower distribution. Right? The narrower distribution is better. Why?
Your values are closer to the mean, so.
Okay, so the values of x bar are on average closer to the population mean, so you're less likely to miss by much. Yes? Everybody happy with that? Okay, now, therefore, the second criterion you want is that if you have a certain amount of information, you use the information to get the distribution that has the smallest variance, smallest standard deviation. Does that make sense? Okay, you can say, well, is it possible to get different standard deviations? Sure. Let's say we're interested in number of cars people own, right? And you're the sample for the student body at UGA, or graduate student body at UGA. Then we could calculate the total number of cars you've all owned collectively, the total group divided by the number of people. But we could equally easily say, we've got 19 observations, but we're going to use the first person we pick, x1, as our estimator. The expected value of x1 is still mu. No problem with that. But the standard deviation for x1 is just the standard deviation of the parent population. Whereas the standard deviation for x bar is the standard deviation for the population divided by n. So here, we're getting a much smaller variance, right? Much smaller standard deviation. While here, we're simply ignoring the last 18 points. Still unbiased, they're both unbiased, but from that criterion, clearly x bar is a better estimator. I know that seems like a contrived example, but at least it's an accurate example. Believe it or not, though, these two are not the core characteristics that econometricians typically want. If you look at this distribution, it might give you a hint as to what is really most popular. As you get a very large sample size, what do you want that distribution to do?
Concentrate around the mean.
Concentrate around the mean. That's exactly right. But you don't necessarily care if the distribution per se is centered around the mean until you get a very large sample size, right? If the mean, if the distribution moves around a little bit while it's slowly but surely centering around the mean, that still is a decent, that's the most important thing, that it eventually does center around the mean, okay? And that last property is called, that's efficiency. The last point is consistency. So this is for efficiency, the last point is consistency. And in words, consistency means that you can, well, if you take some arbitrarily small difference from mu, you can also find an n, sample size, such that the probability of missing by more than that small number becomes arbitrarily small. So essentially it's just saying that in the limit, you're going to hit mu. Kind of key. Okay. We have one slide about alternative sampling methods, simply because I want you to be aware that they exist, not because we're going to do anything with them. Everything we're going to do is going to be based on simple random samples, for the fairly straightforward reason that if you do anything with these formally, you get just ugly math with very little gain conceptually, and most people simply don't use it. But in certain cases it's useful. Stratified random sampling is something you would apply if you have very different classes, for instance. I remember reading about this situation in Norway 150 years ago, where you had people, well, 200 years ago especially, where you had wealthy people, and you had a middle class, and you had poor people, and you saw huge differences in strata, depending on things like, like tuberculosis rates. And the reason was that in poorer places where they didn't have iron-based stoves, they lived in kitchens that were just filled with soot. And actually, the whole house was filled with soot. So sometimes it's easier to get a decent picture of the population if you stratify and you sample from each stratum. And the master of this, as far as I can tell, is the CDC. The CDC will look at both stratum and all sorts of ways and slice and dice the population, and they'll make sure that they get an adequate sample from every single subgroup. And then, of course, you have to turn around and re-weight when you try to come up with estimates for the total population. Cluster samples. If for some reason it's important to you, and typically it'll be because of cost, if it's important that you pick sort of an area, and then within that area choose individuals or observations. It could be apartment blocks in a city, it can be factories. It might be much easier to go to a factory and pick 30 or 100 people than to actually choose 100 people from 200 factories. So cluster sampling is essentially a way to get a reasonably representative sample cheaply. Systematic sampling makes perfect sense to me, in the sense, which of course is always a warning signal, let's say you're dealing with quality control, right? And you pick every 100th. I've solved this at Eaton actually with their superchargers. Every 100 or every certain number they would look at, 5 I think, and inspect them and see whether or not they were up to snuff. The problem is, there are systematic ways where, let's say the machine was just broken and every 100th was completely messed up, but it happened to be one you didn't inspect, and of course you'd never discover that with systematic sampling. There are some weaknesses to it. Convenience sampling. This class, would be a convenience sample. If I decided to give you a survey and we filled it out and decided that this was representative of UGA or of the VA program, whatever, that's a convenience sample because it doesn't get much more convenient than this, right? And believe it or not, it's still the way that quite a bit of sampling is done. Judgment sampling is actually, I think, supposed to alleviate some of the problems with convenience sampling. But basically it means that instead of just choosing everybody within reach, you pick and choose to sort of get something you think is representative of the population. But I have to admit, I really don't trust my own judgment to successfully do that, and I'm not actually dissing anyone when I say I don't trust anybody else's judgment either. So I'm really skeptical on judgment samples. Anyway, but sometimes you don't have a choice. It's better to get some data than no data, right? And actually I've heard it argued that, let's say we were dealing with something like how you react to the color purple. If you see the color purple, does that make it easier to do math? There's no particular reason to think that you as a group are different from any other group with your age demographics and whatnot, right? So it could be argued that that's a representative sample, sort of, but it's certainly not. It's still not a random thing. I mean, there's self-selection going on, there's career choice going on, there's all sorts of ways that we have to be careful. But just so you're aware, there are arguments to be made for pretty much every method. There are 2 points I want to make here. 1, be skeptical, but 2, don't let the skepticism stop you from doing anything at all. Okay? Don't let the perfect be the enemy of the good. Okay. So, that covers what sampling distributions are, specific distributions for the mean and the population. Okay. How is it that we can treat the sample mean as normally distributed? When do we treat the sample mean as normally distributed? When we have 30 or more observations, very good. And then we invoke the limiter. Excellent. In that case, we don't care what the parent population is distributed as, right? Okay. One other way, and that's if the parent population itself is normally distributed. How about the population proportion? I'm sorry, the sample proportion. First of all, what is the sample proportion actually distributed like? Dave, told me last time.
It's binomial.
Binomial. And if we have a large enough sample size?
It could be normal.
Normal. Very good. Remember the cutoff? 5. And what has to be 5? What's that?
Well, populations.
5.
I've got 5 in well population.
Not populations, but your...
Little end of our population, right? Has to be-
No, that's the finite population correction factor. You have to n times p and n times 1 minus p, right? So if you cut the sample up into 2, in 2 groups, each group has to have at least 5. But that's an excellent point, the finite population correction factor. When do you use it? When more than 5% of the population is in your sample. Okay. Okay. Now, one last time, although I'm sure we're going to get back to it next week. What kind of animal is the standard sample mean prior to collecting your sample?
Random variable.
Excellent. Second? It's a random variable, right? You run an experiment, that is gathering your sample, and the process then is you calculate and you find a numerical outcome, and prior to gathering your sample, the outcome is uncertain, but you can assign probabilities. Any questions on the theory? Okay. Okay. All right, let's do some problems. Alright, problem 44. We are told that the mean travel time for individuals in Chicago to get to work is 31.5 minutes. We're further told that the standard deviation is 12 minutes. We're to take a sample of 50 residents. And the first thing we're asked is, what does the sampling distribution of X bar look like, and why?
I was telling him the problem in here.
Oh. Anybody? That's all right. What does the sampling distribution of X bar look like? And why?
It's normal.
Very good. And why? Excellent. because n is greater than 30, we can use the central limit theorem, and therefore we get something like this. Centered around 31.5, right? We're asked, what is the probability that the sample mean will be within plus or minus 1 of the population mean? So plus or minus 1, we have 32.5 and 30.5. So we're asked for this area. How do we find that? Okay, so we want the z-score. And what is that z-score equal to? How do we find it?
You have to calculate the standard deviation.
Very good. We first need to calculate the standard deviation of x bar. 12 divided by the square root of 50.
1.7.
Yeah, good. Okay. So this is just 1 divided by 1.7, or roughly 0.53. 59, yeah. Never tried doing stuff from memory. Okay. And then what? Or maybe I should just ask, is everybody comfortable with the process then? You look up the z-score in the table, you find the area of interest, and apply it. In this case, 0.59, at least in my table, gives me where is it? 0.2224. But of course, we have the same thing on the other side, so that's 2 times 0.2224, or 0.4448. Any questions on that? That's why it's useful to draw it.
The standard deviation of x bar, that's by definition.
Actually, it's a derivation, but not one that we've done, so for our purposes, yes.
Okay.
Other questions? Okay, well, if there are no questions, then I assume 3 is old hat. Yes, no? What would you like me to do to the probability of being within 3 minutes?
Sure.
All right. So what changes?
We're going from 28.5 to 35.5.
Okay. So now we've got 34.5 and 28.5. Right? What else? What else changes?
Three divided by 1.7.
Okay, good. And that's equal to
1.76.
yeah. 1.77 is as close as we're going to be able to observe in the table. So, the probability that x bar minus mu is less than or equal to 3 is equal to the probability that z is between minus 1.77 and 1.77, and since I use the 9th edition table version here, let's use the 10th now. Unfortunately, I haven't actually written that down. Okay, so this piece, if you look up 1.77, you should get 0.9616.
Yep.
And minus 1.77, that should be
0.384.
0.384. Okay. And so this whole thing ends up being 0.9232. All right, so any questions on the tables or distributions, X bar, X? So, the next question then is a classic exam question. What is the probability that a single commuter picked at random will take between 19 and a half and 43 and a half minutes? And what additional assumptions do we need in order to answer that question? Probably shouldn't put that last part there. So,
We have to assume that, well, we have to assume that they are representative of the population, although if we're picking them from the this individual sample, this one commuter, although maybe by definition of them being in the population, we're already saying that.
yeah, you don't really need representativeness, because you can get somebody who takes, an immense amount of time, somebody who has no commute at all, and they're still in the population. How did we know that X bar was normally distributed?
More than 3.
We had more than 30 observations, right? We didn't use anything about the distribution of X itself, right? So we don't know anything about the distribution of X. If you don't know anything about the distribution of X, can you calculate probabilities? No, you can't. That's the additional assumption. You have to decide on some distribution. And you can pick pretty much whatever you want if you're told to pick an assumption, but in reality, you don't want to. If you're just asked what is that probability, and there was no more information, what do you think the correct answer might be, or would be? Zero. Correct answer would be you don't have enough information to calculate it. Impossible to say. It's not just a question that it's not just that you can't say, it literally is impossible to say without more information. The central limit theorem is an amazing tool. It lets you calculate probabilities for the sample mean when you don't know anything about the parent population, except that it has a mean and standard deviation. And that's a fairly remarkable property. Okay. You can pick whatever assumption you want. It needs to come up with an answer. I just have the numbers there to basically to mislead. If you do pick, a normal distribution, then it's fairly easy. The problem is, in real life, you really have to check your assumptions. You can't just assume that everything's normal. Let's look at a sample size problem. 48. Here we're told that the standard error of the mean is 20. And this could be a situation where you're just doing and redoing problems with a standard deviation of 500. First question, how large was the sample? Well, you know that the following is true. So you multiply across and solve for n, you get that n is equal to sigma over the standard error squared. And we can just plug in from there. 500 divided by 20 is 25, squared is 625. So there's 625 observations. Actually, an an exercise that I've done a couple of times is, as you get closer to the election, ask yourself how large the sample size had to be. At least what I found was that until pretty close to the election, CNN would use 300, roughly. But when you got to within a week or two, they switched to 600. It's like they decided it was worth more money to get closer. And notice that the second question, oh, this was A. The second question, in the second question we have not specified a mean. What is the probability that the point estimate was within plus or minus 25 of the population mean? Well, we haven't specified the population mean. So how do we solve that? Well, it turns out that you can just indicate where the population mean is. And you can indicate where 25 units above and below the mean was. Remember, if you know the standard deviation and the standard error, so how do we translate into a z? Z is the number of standard deviations above the mean, right? So how many standard deviations above the mean are we here?
1.25.
Not 25, but
1 1/4.
huh?
1 1/4.
Exactly. The standard deviation of x bar is 20, so it's 25 divided by 20, or 1 1/4. Okay. So the probability of being within 25 is this area. If you look up 1.25, you get 3, 9, 4. So now we've sort of taken one more step into in the direction of differential statistics, right, where we don't know the mean. In this case, we did not know the mean, but we were still able to calculate a probability. Assume now that you presented this to whoever, and your boss or your teammates or whoever, and they decided, well, a standard error of 20 is just way too much. We need a standard error of 10, no more than 10. Excuse me. How can you force that? Or how can you ensure that your standard error is 10? Can you change the standard deviation of the population of interest? No, not without cheating. That's kind of like politicians deciding they really don't like these voters, so I'm going to get some new ones. Which they've been known to do. That's a different issue. So if you look at the formula, if you can't change sigma, the only thing you can change is n, right? Okay. So until this week, I thought there was an easy way and a hard way to do this, and I found out that there was an easy way, a hard way, and a really hard way to do this. The really hard way was suggested as try. Just plug in different values for n. And it's true, you know, eventually you'll find something reasonably close to the standard deviation of 10, but I would not recommend that particular approach. One approach you could do is simply plug in here, right? You already have a way of finding n. So you could simply say, well, n, let's call it n star, has to be greater than or equal to 500 divided by 10 squared, or 2500. Now, normally, you can't specify a standard error and expect to get an integer out here. And and therefore I tend to put the greater than or equal to. But there is a possibly simpler way, which not everyone thinks is simpler. If we repeat this piece, and somebody says, well, we want the standard error to be half as large, just multiply by a half. Well, you can take the 2 inside the square root. So, if you want to have your sample error, standard error, you quadruple your sample size. If you, and by the exact same type of thinking, if you want your standard error to be 1/3, you need 9 times the sample size, and so on and so forth. Which, like I said, not everyone thinks this is an improvement, but as long as you're comfortable enough just plugging in numbers, working with this, that's fine. Questions on that? Finding the right sample size is important because that's typically your main expense, right, in statistics. You either have to buy data or go gather it yourself, and you don't want to spend more money on gathering data than you need, right? Okay. Problem 51. Here we have a proportion problem. So we have a market research that conducts phone surveys with a historical response rate of 40%. It gathers a new sample of 400 numbers, and it wants to know the probability that at least 150 individuals will cooperate and respond to questions. So exam problems would pretty much end there, but since we're learning this, we were given a little extra help. In other words, what is the probability that the sample proportion will be at least 150 out of 400, or 0.375. So the proportion in the population we think is 0.40. We're going to gather a sample of 400, and we want the probability that p bar is greater than or equal to 0.375. Well, first of all, we could do this with a binomial, but we really don't want to, since that would be painful. Can we use the normal approximation? Do we have a large enough sample?
Yes.
And how can you tell?
Greater than 30.
No. That's not for proportion, that's only for sample mean.
Because 0.4 times 400 is greater than 5, and 0.6 times 400 is greater than 5.
There we go. N times P, 400 times 0.4 is equal to 160, which is greater than or equal to 5. And that's what means that's what we need. And 0.4 is less than 0.6, so that's enough to check. So we have the distribution P bar, centered around 0.4. We have 0.375. So we immediately know, well, we want the probability that the proportion is 0.375 or more. So is this number going to be, well, what can you tell me about the probability? Anything? Greater than 0, perhaps?
Greater than 50%?
Greater than 50%, excellent. Because it covers this piece. Okay, so we have a mean and we have a shape, right? And we're interested in the probability that P bar is going to be greater than 0.375. Yes? Okay, what's usually the next step?
Z-score?
Z-score. But in order to find that Z-score, what do we need? We got 0.375 minus 0.4, and what do we divide by? we really need to calculate one other thing, right? And that is standard deviation. With the standard error. Point 4.6, 400, which is a fairly small number, 0.0245, I believe. Yeah. So that z is minus 1.02. Okay, there are different ways you can do this. You can simply imagine flipping it around on its head. And so that's the probability that z is less than 1.02. And if you look up 1.02 in your table, you find 0.3463 in the 9th, 0.8461 in the 10th. But regardless, it's 0.5 plus 0.3461 or 0.8461 in all. So roughly an 85% probability that you'll get a response rate of 37.5% or more. Any questions on that? I know we're rapidly approaching saturation, but I still want to make sure that we're on the same page. Okay. Um, 50, actually. Okay, so on June 13th in 01, 30.5% of individual investors were bullish on the stock market. We assume that 200 investors are sampled. So we have a proportion of 0.305 in the population and 200 in our sample. Is that a large enough proportion to use the normal approximation? I'm sorry, a large enough sample size? What is greater than 5? You're quite right, but we need to know what is. Any recollection?
Is it the standard error?
No, it's not the thing there.
N times P?
9 times B. 61. Right? And we don't need to worry about the 1 minus 30% because that's much lower. So this is roughly normally distributed. The mean of 0.305 and a standard deviation of P1 minus P over N. So that's 0.305 minus 0.305 divided by 200, which is roughly
What was our tip off? This was a check for the 5 as opposed to the 30 again in this one.
what's that?
What was the tip off? That this was a check for the 5 as opposed to the 30, the normal? What was the problem?
Under A, it says show the sampling distribution of P bar, the sample proportion of individual investors. So when you know that it's a proportion. So now we're showing the distribution, probability that the sample proportion will be within 0.04. What's the next step? So we could draw this, right? 4%, that's standard. 0.345 and 0.265. So we're looking for this area. The next step is to find Z. Okay? So we take 0.345, subtract 0.305, divide by 0.033, and that's approximately 1.23, and minus 1.23. You notice we're doing the same thing again and again, right? So hopefully that'll stick. All right. So we look that up, and that's equal to. We look up 1.23. You find that this area is 0.3907, which means that this is 2 times 0.3907, or 0.37814. And by direct analogy, the probability that the sample proportion is less than or equal to, or the sampling error is within 2 percentage points. Well, we can do that out here. So 0.325, 0.285. Actually, even before I do anything else, you should be able to tell me something about that probability, yes?
It'll be smaller
Then,
than 78%.
right, it should be smaller than 78%. Very good. So we translate, we find 0.02 or 0.033, which is roughly 0.61. And that gives us 0.2291. Which is 0.4582. So as you notice, we built an enormous amount of figuring out if we can use the normal distribution. Shockingly, we can, and then translating it into a Z and specifying the probability. All right, any questions on sampling distributions, especially the ones that turn into normal? No? Are there any, can you give me just a quick update on your projects? Maybe less different subjects, but anybody? Just 30 seconds or